metals. Group 1 are the most reactive metals. Group 7 are the most reactive non-metals, with the reactivity decreasing down the group. Hence, fluorine is the most reactive non-metal, followed by chlorine in this group 7, followed by bromine, and then iodine. So it comes in this order. Fluorine most reactive, followed by chlorine, followed by bromine, and followed by iodine. Okay? Alright. And also they exist as diatomic molecules. So you will never see iodine written like this or bromine written like this. It is always what? As diatomic gases. Okay? With the exception of bromine. Bromine is not a gas actually, it's a liquid. Okay? But they are usually diatomic. Now, this is for group 7. But in a broader sense, if I include other groups, actually oxygen is more electronegative than chlorine. Here now I'm considering only the group 7 non-metals. So if I should consider the whole table holistically, then we have fluorine is greater than oxygen, greater than chlorine, greater than bromine, and greater than iodine. So this is the decreasing order of electronegativity. Hence, fluorine is the most electronegative non-metal. Alright. So what about their colors? Now, as something is expected, as they go downwards, they change their state. So the first two, fluorine and chlorine, are gases. Bromine is a liquid, and iodine is a solid. Okay, fluorine will give us is yellow. Chlorine is greenish yellow. Okay, and then bromine is gas, some liquid. Okay, liquid. Then iodine is solid. It's a black solid. It's black in color. So these are some of the important features. Of course, you know when we have three states of matter: gases, liquid, and then solid. In gases, the force of attraction is not really that pronounced. But as you come closer to liquid and to solid, there's increasing force of attraction. So the force of attraction is getting more. So solids have more force than liquids, and liquids more than gases. And because of this force of attraction, since fluorine is a gas, since as we are going downwards, they are becoming solid gradually. It therefore means that as you go downward, the melting point and the boiling point also should be increasing because the force is gradually increasing. This is a solid. A solid should have a higher melting point and a higher boiling point than the liquid. Why? There is higher force. The particles are closely packed because of the force of attraction. Hence, it will require a more heating energy to split them and separate them apart. Alright. So, that is for group 7. Then let's now take a tour to group 8. There's no much about group 8, just that they are very, very stable. Now, why are they stable? The primary essence why elements undergo reaction is to attain stability. But these elements are already stable, so they don't need to attain stability. How do we know they are stable? Because in their outermost shell, there are 8 electrons, with the exception of helium that has 2 electrons. Helium is the second element in the periodic table. So it is the only duplet element. It is only the element that is stable in the duplet states. The rest in group 8 are stable in the octet state. Although helium is only placed here because of convenience. Because if we should follow the rule that says that elements should be placed in a group based on their valency, helium will have been placed in group 2 and not group 8. Okay? But for the properties it shares between 8 elements, that is the reason why it is placed in group 8. Now, we have looked at the history, the blocks, the groups. Let's now currently look at also at the configuration of elements, electronic configuration of the element. So this is how we configure elements. like I just showed to us. But there's something I want to point out for us. For example, I want to configure an element like calcium, which is 20. Calcium is 20, which I'm supposed to get 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. Let's count this up to 20. So if you are given an element and you don't know it, and they ask you what element is this, count these numbers as which are the superscript. Add them together, whatever number it gives you, trace it in the table, that's the element. So let's check. 2, 2, 4, 4, 6, 10, 12, 12 plus 6, 18, 18 plus 2, 20. So we know it's calcium. I can write calcium like this, but for sake of convenience and to be fast, what is the nearest stable structure close to calcium or before calcium? This is calcium 20. If you check, the 18th element is argon, is stable. So we can use the structure of argon to configure calcium. How do we do it? This is argon. Argon is 18. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. So 2 plus 2 is 4, plus this is 10, plus 2 is 12, plus 6 is 18. This is argon. Which means from here like this are the same. Just these are the separate, that is not there. Hence, calcium, which is 20, can also be configured using this pattern. So this is what calcium. Please take note of this, because when I'll be configuring the transition element, I will fall back to what I just said here. Alright? Good. Let me just leave it there for now. Let's quickly look at the transition methods. Transition methods. Okay. Why are they transiting? Of course, the transition methods, they are found between group 2 and group 3 in the table. This is group 2, this is group 3. This is where we find them. We have the first series from scandium to zinc, which is from 21 to 30. And we have the inner series, which are made up of the lanthanines and the actinines series. So, why are they transition elements? What are their properties? The properties of this element. One, they have variable oxidation states. The oxidation number of an element is the charge that element appears to carry. That's the oxidation number. Is the charge it carries. And these elements, which are the transition series, they have variable state of oxidation number. You could see, for example, iron in the +2 state. Iron is 26, if I'm not mistaken. You could see iron also in the +3 state. Variable. There are some that don't have up to 3 states or even 4, but iron has 2. Now, iron in the +2 state is the reduced form. In the +3 state is the oxidized form. So converting iron from the +2 form to the +3 form, such reaction is called oxidation reaction. While the reverse is a reduction reaction. And the iron in the reduced form has the color green. The oxidized form has the color brown. So why do they have variable oxidation states? It's dependent on their configuration, okay, which I have not yet explained. But let me just throw a bit light on it. They can take electrons from the 4s and also from the 3d in pairing. That's why they have variable oxidation states. Okay, the electrons are available from both orbitals, from both blocks. Apart from having variable oxidation states, they also have they form complex colored ions. They form colored ions. An example has just been given to us. This is a colored ions. Another example to it again, we have copper 2+, which is blue in color. With the exception of scandium and zinc, okay, which are colorless. Scandium is colorless, zinc is colorless. But copper is blue, iron is green in the +2 state, and the brown in the +3 states. So these are some of the colored ions formed by the transition series of metals. Number 3 is their ability to form complex ions. Number 3, they form complex ions. What is a complex ion? A complex ion has a central core, C-O-R-E, of the transition metal. For example, we could have iron here, to which other groups are bound to. These groups which are bound to the central metal are known as either Lewis acids or Lewis bases. Lewis, L-E-W-I-S. I'll bring the lecture on Lewis acids and bases as we continue in this journey. These Lewis compounds are also called ligands. So the ligands, for example, let me use OH, okay? OH, 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 that are bound to this ion are held by a kind of bond called dative covalent bond or coordinate covalent bond. So this is the formation of a complex ion. Alright, that is another property of the transition series of metals. Number 4 property of these people is that they exist as paramagnetic compounds, or they exhibit paramagnetism. Paramagnetism. What does it mean? Paramagnetic compounds are compounds that are weakly attracted to a magnetic pole, while the opposite is diamagnetic. They are well attracted, attracted. But for paramagnetic, they are only partially, weakly attracted. And these metals, they exhibit this phenomenon or this property. The 5th property here is they have partially filled d orbitals. So this will now bring me to their configuration. I just said they have a partially filled d orbital. They have partially filled d orbital. Let's see how we get their configuration. So 21, these are the elements, the transition metals, the 21st, 22nd, 23rd, 7, 8, 9, 10. Okay, so we have scandium, titanium, vanadium, chromium, manganese, iron, nickel, cobalt, copper, and then we have zinc. Alright, so this is our configuration. So after configuring them, we will now appreciate the reason why we said they have partially filled d orbitals. Of course, scandium is 21, and the closest stable electron close to it is argon. So 21, if you have argon removed from it, argon is 18, we are left with 3. So that 3, if we come here, this is argon. Argon stopped at 4s. No, argon stopped at 3p6. Okay, because this is 2, 2, 6, 10, 12, 18. So if this is where argon stops, these are the next orbit blocks to it. So what do we add to it? Normally, from what I drew here, 4s comes before 3d. Alright? But in configuring these transition metals, take note that 3d should come before the 4s. So we have 3d and we have 4s. So just repeat this for the rest. Okay, 3d, 4s, vanadium, 3d, 4s, chromium, 3d, 4s, manganese, iron, 3d, 4s, nickel, 3d, 4s. So you may be asked in exam, to identify the properties or which of them is not the property of these metals. So I listed 5 which you should know. 4s. Then argon, 3d, 4s. So let's see their configuration. What happens? 3D comes before 4s as opposed to what I have written here. Alright. When you are filling them, this is so argon is 18 and scandium is 21. So 18 minus 21 was still with 3 electrons. So the 3, 2 will come here, 1 here. So first feed this S before you come here. So 2, 2, so 1 is 2. 2, 3, 5, 5, 6, 7, 8, 10, 10, 2, 1, 2, 2, 2, 2, 2. Alright? I know somebody might be wondering how I got those values. It's just constant practice, then it will be used to you. So what I want to shed light on is you should take note of chromium and then take note of chromium and then copper. Why? Let's look downwards. 1, 2, 3. I'm supposed to get to 4, but there's no 4. So that is according to chromium. Thereafter 5, 5, 6, 7, 8, 9, 10. But there's no 9. Instead there's a 10. That's what we have here. Since there's a problem occurring at the D block, it will reflect at the S side. So let's check. All the S are 2. 2, 2, 2, 2, 2, 2. Except here. Yes, 1. Yes, 1. So for those that have anomalies, which means they have rolled from their S orbital to the D, so their S will now become 1. So zinc is argon is 18. 18 plus 2, 20 plus 10, 30. Copper is 29. 29 plus 10, 13, 28, 9. This is 18. 18 plus 10, 28, 29. Okay? Then this is chromium. Chromium is 24. 18 plus, this is 6, give us 24. So when configuring them, the only place you have to take note of is chromium and copper. The other are just going to follow suit. So chromium, we have the 5 taking 1 from the D, taking 1 from the S. Now, why do I say in that fifth property that they all have incompletely filled d orbital? When you check all the d orbitals, they are not filled completely. Why are they not filled completely? Because the d orbital can accumulate a maximum of 10 electrons. But we have what? Them not up to 10. The only place where they have up to 10 is what? Is copper and zinc. Okay, so they are kind of want to behave as if they are not true transition metals, as if they are a typical transition metals. Alright. Okay, then having said that, let's now quickly look at the families of elements. The families of elements. But prior to that, let's first look at the trends that occur, or the periodicity. The first trend I want to discuss is atomic size, also known as atomic radius. What is the atomic size? The atomic size, let's see, we have something like this. This iodine, so this iodine atom covalently bonded to another iodine atom to form iodine molecule. The nucleus, this is the distance between the two nucleus. So the atomic size is actually the distance between the nuclei of two same, S-A-M-E, same or the same, covalently bonded atoms.